Okay, so recording start. Okay, good morning, all of you. So, welcome to the new topic, that is electron beam machining process. Today, we are going to see the electron beam machining process, as this is a thermal energy based non-conventional machining process. Okay, electro-thermo you can call, or thermoelectric. So this is second one, because last lecture we have seen the laser beam machining. So today we will go for electron beam machining process. Now, in this electron beam machining process, actually the material removal is happening due to the, that means we can call, there is a bombardment of high velocity stream of electrons on the your workpiece surface. So these electrons are bombarded on the your workpiece surface with a very high velocity, around 60% velocity of that sunlight. So because of that bombardment of the electrons on the workpiece surface of the workpiece surface, so the material from that workpiece surface, it will remove, or material that will remove into a small, from that small area of your workpiece surface. And and that material removal action means that due to the bombardment of free electrons, the melting will happen from that workpiece surface, small workpiece surface, and melting and the vaporization. Okay, so due to that two actions, material removal will take place, and during that time, temperature of that surface is going to rise up to the very high temperature. Okay, so temperature of that small area where high stream of the electrons are going to bombard, no, so that localized area temperature is going to rise to a very high temperature. So material on the workpiece surface melts and vaporizes, and machining is going on. So this is the basic funda behind this electron beam machining. I repeat, material removal action is going to take place due to bombardment of high velocity stream of the electrons on the workpiece surface. Okay, bombardment of high velocity stream of electrons on the workpiece surface. Okay, and due to that bombardment on the small area of your workpiece, their temperature of that localized area is going to increase, and due to that melting and vaporization will take place, and from that machining is happening. Okay, so this process actually it is used for the machining thousands of holes on a thin sheet. Okay, okay, if you want to go for the machining of a holes, again that holes means the thousands of holes on a thin sheet. Okay, which is used in the aerospace industry, that thin sheet along with that small holes. Okay, so this thousands of holes on a thin sheet we can machine using this electron beam machining process. Okay, and this type of application normally it is used in aerospace industries, then food processing industry, cloth industry, and very high aspect ratio for making of very this thousands of folds. Now we require the high aspect ratio. So thousands of folds on this workpiece surface, irrespective of the material property. Here we are not going to consider the material properties, that workpiece material property, like metallurgical property or mechanical property of the machine. Okay, so this material, maybe here, as we are going to use electric energy, so this material may be electrical conductive or the electric non-conductive. Okay, or maybe ceramic, metal, or any kind of metal. Okay, any kind of metal, because here electrons we are using on the workpiece, so that workpiece metal may be electric conductive or electric non-conductive, or maybe ceramic metal or any kind of metal, any kind of ceramic it was. Okay, so here there is a filament which is, I'm going to explain with the help of that diagram also. So here, just for the introduction purpose, I am explaining. So here, there will be the one filament which is heated with the very high temperature. So because of this heating of that filament, so electrons that emits from that cathode, From cathode means what, that cathode filament. Okay, on this the filament may be heated from the radiation from the another body. So from that radiation from another body on that solid block of your cathode, no, on the solid block of filament you can call. So it can be generated that electrons. So these electrons what are generated, no. So these electrons emits from that your cathode and cathode filament, and it from that then your electrons going to pass through a magnetic lens. Okay, and that will why that magnetic lens is required, because we have to send that electrons on a workpiece surface. Okay, small workpiece, that small surface of the workpiece. So to concentrate that electrons on that small surface of the your workpiece, we require that magnetic lens. Okay, to coincide or to concentrate or to reduce the diameter of the electron beam. Okay, so we'll get the high temperature, and then it will bombard on your small surface where we want to go for the machining of the your workpiece surface. Okay, so this is just a introduction. Okay, now we'll discuss in detail about this electron beam machining. So electron beam machining process, in that there are two types of methods are used. Okay, there are two types of methods are there. One is the thermal type. Okay, as I have shown that, you can see arrow also I have given. One is the thermal type and another one is the non-thermal type. So in non-thermal type, electron beams are used for generating chemical reaction. In non-thermal type of electron beam machining, there electron beams are used for generating the chemical reaction. So for generating the chemical reaction, the electron beams are used. Okay, so this non-thermal type we are not going to discuss. Okay, because we are not considering about the chemical reaction. So here we are not going to consider, we are not going to discuss this non-thermal type. Okay, so we are going to discuss only thermal type of electron beam machining process. Now in this thermal type of thermal type electron beam machining, cathode is heated to a very high temperature. Okay, cathode is heated to very high temperature. So this stream of, I will show the diagram also. Now we can see here is the cathode grade. So in this thermal type of electron beam machining, cathode is heated. Okay, cathode is heated to a very high temperature. So this stream of large number of electrons comes as a small diameter beam, that is electron beam. Okay, you can see from the by hitting that cathode, no, cathode grade, we will get the stream of high temperature, that a large number of electrons will get from this small diameter. Okay, so this stream of large number of electrons, no, then emit which is we got or emitted by that cathode, we will get from that heated cathode. So to heat that cathode, we require that source, our power source. So again it comes out of as a small diameter beam. You can see I have shown that small diameter beam. So it moves toward the workpiece with a very high velocity and it bombards. Okay, it bombards on this workpiece. Okay, and the machining going on. Now how that machining will going on? Due to the bombardment of these electrons on a very small localized area. Okay, माझ्या काय टोटल एरिया दिसतोय बघा तुम्हाला, हा ब्लॅक शेडेड वाला, तर हा वर्कपीसचा सरफेस आहे. पण त्यातलं काय करायचं, मला स्मॉल एरियावरच फक्त, म्हणजे त्या स्मॉल एरियाला मी म्हणतो की लोकलाइज्ड एरिया, आणि तिथंच मला होल पाडायचं किंवा ड्रिल पाडायचं. तर मी काय करणार, तिथंच फक्त इलेक्ट्रॉन्स बंबार्ड करणार. आणि इलेक्ट्रॉन्स मला कुठनं भेटलेत, हाय व्हेलॉसिटी इलेक्ट्रॉन्स, तर मला त्या कॅथोड ग्रेड पासून भेटलेत. आणि ते कॅथोड ग्रेड म्हणजे काय, तर हिटेड कॅथोड ग्रेड आहे ना, जेणेकरून तिथनं मला स्ट्रीम ऑफ द इलेक्ट्रॉन्स भेटलेला आहे. ओके. आणि ते स्ट्रीम ऑफ इलेक्ट्रॉन जर मला कॉन्सन्ट्रेट करा असेल, म्हणजे काय एकदम स्मॉल डायमीटर मध्ये जर घालवायचे असेल, तर मी काय वापरणार, तर माझ्याकडे लेन्स वापरणार. ओके. सो you can see this block. So these are the magnetic lens. Okay. So I repeat, whatever the stream of the large number of electrons which we got, or the from the heated cathode, that means the stream of large number of electrons emits from that cathode, from that heated cathode. Okay. So it comes out as a small diameter beam, and then it moves toward the your workpiece with a very high velocity, and then it bombards. Okay. And then machining is going on due to that bombardment of these electrons on the very small localized area of your workpiece. So as that electron beams is bombarded on a very small localized area, then huge amount of temperature is generated on the surface of your workpiece. Okay. बॉम्बार्डमेंट झाल्यानंतर त्या वर्कपीस सरफेसचं तुमच्या काय होणार, टेम्परेचर वाढणार. ओके. अँड सो मसनिंग इज गोइंग ऑन ड्यू टू दॅट मेल्टिंग अँड वेपरायझेशन ऑफ दिस मटेरियल फ्रॉम द युअर वर्कपीस सरफेस फ्रॉम ए व्हेरी दॅट स्मॉल लोकलाइज्ड एरिया. कळलं. बॉम्बार्डमेंट झाल्यामुळे काय होणार, त्या लोकलाइज्ड एरियाचं टेम्परेचर वाढणार. ह्यूज अमाऊंट ऑफ टेम्परेचर इज गोइंग टू जनरेट. दॅट मीन्स rising of the temperature of that localized area of the your workpiece will happen. आणि ते जर टेम्परेचर वाढलं तर काय होणार, तर मेल्टिंग अँड वेपरायझेशन ऑफ दिस मटेरियल फ्रॉम युअर वर्कपीस सरफेस फ्रॉम युअर व्हेरी लोकलाइज्ड एरिया विल इनक्रीज, अँड थ्रू दॅट मेल्टिंग अँड वेपरायझेशन मटेरियल रिमूव्हल विल टेक प्लेस. ओके. नाव so what from that kinetic energy of the your this electron beam, no, that is used for that machining. Okay. बरोबर का. त्या बीमचं कुठलं बॉम्बार्डमेंट होतं म्हणजे काय, हाय वेलोसिटी मीन्स व्हॉट, इट हॅव्हिंग द सम ह्यूज अमाउंट और हाय अमाउंट ऑफ kinetic energy. So this kinetic energy of that electron beam is used for the machining, to take place that machining, and which convert this kinetic energy of the beam, that electron beam, high velocity electron beam, converted into the heat energy. Okay. बॉम्बार्डमेंट झाल्यानंतर म्हणजे बॉम्बार्डमेंट व्हायच्या टाइमापर्यंत काय होतं, माझ्याकडे हीट एनर्जी होती त्या इलेक्ट्रॉन बीमची. बट वन्स इट विल बॉम्बार्ड ऑन दॅट लोकलाइज स्मॉल एरिया ऑफ द युअर वर्कपीस, नो, so it is going to convert into the heat energy. So it can produce the holes of different shapes, that means the machining. Because of the heat energy is going to due to that heat energy, melting and vaporization will take place. So any kind of shape other than the circular also can be generated by the deflecting this beam at a certain angle. Okay. So please remember this point also. Okay. Any kind of shape other than the circular. Okay. Circular जर मला shape पाहिजे असेल तर आपण straight forward beam pass करावं लागेल ना. But other than this circular shape, we can generate any kind of shape. Okay. By deflecting our beam at any certain angle. So workpiece material can be conductive. Please remember again this point, I am repeating here, workpiece material can be conductive as well as non-conductive. Any kind of workpiece can be machined irrespective of their hardness, that is the mechanical and the metallurgical property. Okay. So that kind of material, workpiece material can be machined by this process. Okay. And also another thing is that for this electron beam machining, this is the only one process from the advanced machining process, that is for this process vacuum is required. Now why vacuum is required, that I am going to explain. Okay. Please remember this point. In MCQ this question may will come. Okay. May come. Vacuum is required for only electron beam machining process. Okay. दुसऱ्या कुठल्याही प्रोसेसला व्हॅक्यूम लागत नाही. Now for what purpose this vacuum is required, that I will go. So you can see this is our machining chamber. Okay. You can see workpiece is there and the work holding device can whatever the rectangular shape is given, no, that here cursor is there, no, so viewport is there. So this is our machining chamber. Okay, so this is a machining chamber, and that should be vacuum chamber, because whatever this electrons beam when it travels, no, if air is there into that chamber, no, so it will collide on the air molecule. काय होणार, इलेक्ट्रॉन ज्या टायमाला आपल्याला त्या तुमच्या मशीन चेंबर मध्ये आल्यानंतर जर एअर असेल तर काय होणार, so if air will be there, no, then your electron beams is there, no, so that will collide on the air molecule, correct? So its strength will be reduced, whatever the electron beam strength is there, no, so it will reduce if air molecules will be there. So that is why this vacuum is generated into that your machining chamber. And also कळालं, हे महत्वाचं आहे बरं का, व्हॅक्यूम का वापरायचा. जर आपले एअर नॉर्मल वर्किंग कंडिशन जर तिथं असेल तर काय होणार, एअर मॉलिक्यूल मध्ये येणार तुमच्या इलेक्ट्रॉनच्या मध्ये, आणि ते इलेक्ट्रॉन त्या बंबाड किंवा कोलाइड होणार, आणि त्या कोलाइड जर झाले तर काय होणार, जे स्ट्रेंथ असणार तुमच्या इलेक्ट्रॉन बीमचे ते रिड्यूस होणार आहे. ओके, आणि त्यामुळे तुमचं काय मशीनिंग प्रॉपरली होऊ शकणार नाही ना, स्ट्रेंथच नसेल तर कसं आहे होणार नाही. सो व्हॅक्यूम इज रिक्वायर्ड or vacuum is to be generated in that your machining chamber. Please remember this point. Also this cathode, it is used order we have used, no, this cathode you can see here. So it is a that cathode is, it is used as a tungsten cathode, tungsten cathode, and it is used if air is there, so it will immediately it will be oxided. Okay, so to reduce or to avoid the oxidation of this tungsten filament cathode, so this vacuum chamber is required. Okay, vacuum chamber is required. Okay, okay, I repeat, to reduce the or to avoid the oxidation of this tungsten filament, or that cathode is there, no, that is called the tungsten filament. Filament, it is made of the tungsten, so that tungsten filament cathode is there, no, so this vacuum is required for that purpose. So beam size, this diameter of this beam size should be less than diameter of the your hole to be produced. Okay, जे तुम्हाला होल प्रोड्यूस करायचंय त्या डायमीटर पेक्षा कमी तुमचा इलेक्ट्रॉनचा डायमीटर पाहिजे, म्हणजे इलेक्ट्रॉन बीमचा, आय एम कॉलिंग एज इलेक्ट्रॉन बीम, नॉट ओनली सिंगल इलेक्ट्रॉन. सो that ejection of the molten material, how this molten material is ejected, or the molten vaporized material is ejected from the workpiece surface, so that question may arise. Okay, so at the back side of your this workpiece is there, no, so backing material is used. So after machining on the your this top surface of the workpiece, no, so when it reaches to the bottom side of the your workpiece, then it also vaporizes that backing material, this backing material. Okay, so this backing material also vaporizes, so it comes out as a high pressure. So this backing material it comes out as a very high pressure. Okay, so while coming as a high pressure, it also eject the this your molten or the vaporized material on your workpiece surface. So it expels that your molten or the vaporized material from the workpiece surface. So at the back side of the your workpiece surface, there is a backing material is used. So that is why this backing material is used, because we have to expel or we have to take out the what are the molten material. Molten metal means what, or vaporized म्हणजे काय, जे मटेरियल रिमूव्ह झाले ना ते आपल्याला बाहेर काढायचं आहे ना, त्यासाठी आपण काय करतो, जर एक बॅकिंग मटेरियल वापरतोय तिथं, आणि ते बॅकिंग मटेरियल म्हणजे काय, तर हाय प्रेशर असणार आहे, हाय प्रेशर न ते बाहेर येणार आहे. ओके, सो with the help of that backing material you can take out the that molten or the vaporized material, जे रिमूव्ह झालेलं मटेरियल. Okay, so again non-circular holes also can be generated by this as I have mentioned, or any kind of shape, any kind of shape of the workpiece can be generated by this electron beam machining. So you can make, you can you can keep fix the beam, and you can travel to your workpiece also. Okay, if you want to go for the any inclination holes, okay, so that time you can fix your electrons beams, no problem. But you can travel your workpiece with the help of that CNC table, that computer numerical CNC table. Okay, you can place your workpiece on the CNC table, and you can generate any kind of complex shape, or you can move your beam on your workpiece surface using the CNC table also. So in both the way, you can generate any kind of non-circular holes also on your workpiece surface. So circular big holes can be generated also. You can move your beam along the perimeter of the circle, so that you can generate the bigger size holes also. Okay, so here whatever I have given the explanation, so it's that flow chart I have shown here. Okay, how the bombardment uh, will take place on your workpiece surface, and then how that bombardment of electrons will increase the temperature, and due to that melting and evaporation will take place. Then and that heat energy, how you will get that from the your kinetic energy of the beam. Okay, and that can be produce the holes. Okay, and here please note that again one more question for the MCQ, that your beam electron beam size should be less than the desired hole size. Okay, which we want to produce on our workpiece. Okay, and your workpiece may be conductive as well as non-conductive, or ceramic, or any metal. Okay, and here again one more thing, don't forget, vacuum is required in the machining chamber. Okay, again that vaporized vacuum metal, it will comes at a high velocity, and along with that it will expel the molten workpiece metal. Okay, and if you want to go for the non-circular hole, then you can move electron beam by a computer control along your hole diameter, so that means sensitive. ओके, जर तुम्हाला इलेक्ट्रॉन बीम सेट ठेवायचा असेल तर तुमचा वरपीसचा टेबल तुम्ही मूव्ह करू शकता, सीएनसी टेबल. Otherwise you can keep your work table fixed, and you can move your electron also, no problem. In both ways it is possible. Now this is a schematic diagram of the electron beam machining. Okay, yeah, you can see here. Okay, this is a cathode. Once again I am repeating. This is cathode. So you can see here, this is a cathode. Okay, so this cathode filament, it is actually heated up by using the high voltage lead. High voltage lead. That means the supply of the our power supply. So this cathode filament we have to heat with the help of this high voltage lead. दिसलं तुम्हाला त्याला कनेक्शन. ओके, so there is a high voltage lead is there. So using this high voltage lead, this cathode is actually heated up. Okay, so this electron beams, that means the stream of electrons are coming outside from this cathode filament because of a repulsion force from the cathode. Okay, how that electrons are generated? So the answer is that because of repulsion force from the cathode, that stream of electrons are going to come outside of that cathode filament. Okay, and that cathode filament, it is made up of the tungsten material. Okay, so electrons are negatively charged, or here this cathode also they are negative terminal of your power supply. Correct. Here anode also is there, that is a positive. You can see cathode is a negative terminal, and the anode is a positive terminal of your power supply. So these electrons are expelled with the very high velocity, and it is coming towards your anode. Okay, anode दिसते तुम्हाला. Okay, जांभळा कलर. Okay, so these electrons are expelled with the high velocity, and it is coming towards your anode. So it is attracted towards the anode here. Correct. So this is anode. Okay, so as it is attracted towards the anode, and it is also expelled by the this cathode, so it generates a high velocity, very high velocity. So it is around 60% of the light velocity. Yeah? Velocity of stream of velocity stream of electrons. Okay, velocity of stream of electrons is very high, and it is around 66% of the velocity of the light. Please note that this also. Okay, so it is passed through this wall coil. You can see here. Here wall coil is used. This whatever the stray electrons are there, no, so that will, it is actually filtered. So the stray electrons are filtered through this wall. Okay, wall काय वापरायचं कशासाठी? Okay, wall coil. So to filter that electrons. Okay, stray electrons are filtered through this wall, and you can see this what is happening inside this vacuum chamber. So you can see using this optical viewing system. Okay, this one, optical viewing system, this is used. From this you can see inside your this vacuum chamber what is going to happen inside this. जे तुम्हाला हे बॉर्डर दिसतंय हे पूर्ण हे खालचा आणि हे म्हणजे काय तर चेंबर आहे आपला, मशीन चेंबर त्याला म्हणू शकतो. हे सगळं व्हॅक्यूम असणार आहे. ओके, डोंट फॉरगेट दिस. So you can see this one can see what is happening inside that vacuum chamber. So for that purpose this optical viewing system is used. Okay, प्रत्येक कंपोनेंट सांगतो मी का वापरलाय. ओके, आता तर आपल्याला माहित झालं हाय व्होल्टेज ग्लिड का वापरलाय, कॅथोड रेड कशासाठी ग्लिड दॅट इज टंगस्टन फिलामेंट, दॅट एनोड कशासाठी, वॉल कॉइल कशासाठी, ओके, ऑप्टिकल व्ह्यूइंग सिस्टम कशासाठी. देन विल गेट द स्ट्रीम ऑफ रेड कलर, stream of electron, high velocity stream of velocity, stream of electrons. Got it? Now this electrons is passing through this magnetic lens. You can see this is a magnetic lens. Okay, this is magnetic lens. So this is a magnetic lens, and the working principle of this magnetic lens is that so it actually concentrates all the electron beam into a certain point. Okay, सगळं इलेक्ट्रॉन बीम काय करणार ते with the help of magnetic lens we can concentrate on a only certain point. So it reduces the diameter of the your electron beam. Okay, and passing towards the your workpiece. Okay, towards your workpiece. So it concentrates into a smaller diameter beam. You can see. Okay, smaller diameter beam. So after this magnetic lens, no, it passes through the deflection coil, and after passing through this deflection coil, it falls on the workpiece surface into the very very small area. Okay, आता इथपर्यंत आलं. So when it falls on this workpiece surface into a very small area, small area. So because of this bombardment of the high velocity electrons, it melts and vaporizes the material. And okay, bombardment झाल्यानंतर काय होणार आहे, कायनेटिक एनर्जीचं कन्व्हर्जन हीट एनर्जी मध्ये होणार आहे. हीट एनर्जीचं कन्व्हर्जन हीट एनर्जी मुळे काय होणार, तर त्या सरफेसचं टेम्परेचर वाढणार आहे. आणि ड्यू टू राइज ऑफ द टेम्परेचर ऑफ दॅट स्मॉल एरिया, melting and vaporization of that material will take place. That means the removal of the material will take place. Okay, and at the back side of this workpiece, no, I repeat, at the back side of this workpiece, this chemical backing material is used. I repeat, at the back side of your workpiece, chemical backing material is used. So when these holes actually extended toward the end of your workpiece, this backing material also. Okay, so because of fitting, this high velocity gases are generated. Okay, backing material जे chemical backing material वापरले ना, ते high velocity मुळे काय होणार, that at the end of your workpiece, okay, holes. Okay, actually whatever that holes are actually extended towards the end of your workpiece. So this whatever the backing material is there, no? So also because of that heating, high velocity gases are generated. High velocity gases are generated. Okay, from the your backing material, chemical backing material, high velocity gases are generated. So this gas, when it is coming outside with very high velocity, okay, with a very high velocity, then it expels whatever the molten metal is there, no? Molten metal means what? Vaporized material, जे remove झालेलं material आहे. So it will expel because of that high pressure, very high pressure of the your backing material. Okay, it expel whatever the molten metal is there, no, at the hole. Okay, at the hole. So whatever this molten metal is there, no, so it also expels that molten material. Okay, now, so whatever this recast layer, whatever the that molten material is there, no, or whatever it is redeposited on the workpiece surface. So this recast layer is that molten materialचं जे लेअर तयार होतं ना त्याला recast layer म्हणायचं. So whatever it is deposited on the your that recast layer, no, so that is deposited on the workpiece, no, surface. So this recast layer can be reduced by this chemical backing material. Okay, कारण की chemical backing material काय होणार आहे तर हाय वेलोसिटी तयार होणार आहे. ओके, आणि त्या हाय वेलोसिटी गॅसेस तयार होणार ना, सॉरी, हाय वेलोसिटी गॅसेस तयार होणार आणि त्यामुळे काय होणार, हाय प्रेशर न ते बॅकिंग मटेरियल मोल्टन मटेरियल सुद्धा बाहेर काढणार. ओके, जे रिकास्ट लेअर आपण रिड्यूस करू शकतो. ओके, बाय दिस केमिकल बॅकिंग मटेरियल. सो दिस एंटायर chamber, it is actually made up of this chamber, no, what I have shown the border, no, that is entire chamber. It is actually made vacuum to reduce the for what purpose vacuum is used? To reduce the possible collision of the electrons with the air molecule. Okay, please don't forget this point. कळलं आहे, समजलं सगळ्यांना? Have you understood? आता कळलं प्रत्येक पॉइंट कशा का वापरलाय आपण. Understood or not? Hello, आवाज येतोय का? Hello, hello, am I audible? समर्थ चव्हाण, समर्थ.
हाँ यस सर
हा हा सांगा रे. ओके, अंडरस्टूड. आदित्य मोटेवार, हॅव यू गॉट द वर्किंग प्रिन्सिपल ऑफ दिस इलेक्ट्रॉन बीम मशीनिंग? के प्रत्येक पॉइंट महत्वाचा आहे. एक तर पहिली गोष्ट तुम्हाला कळायला पाहिजे की इलेक्ट्रॉन कुठून तयार झाले. त्यासाठी आपण कॅथोड वापरला, कॅथोड ग्लिड म्हणा किंवा फिलामेंट. त्याचं मटेरियल काय तर टंगस्टन आहे. ओके, देन 5 I have used that wall coil, then optimum view system का वापरतोय, मॅग्नेटिक लेन्स का वापरतोय, व्हॅक्यूम मध्येच का पाहिजे ही पूर्ण मशीन चेंबर. ओके, व्हॅक्यूम का पाहिजे. ओके, आणि ते मोल्टन मटेरियल जे आहे ते बाहेर कसं काढायचं हे आपल्याला माहित पाहिजे ना. ओके, हॅलो युवराज सेलार, हॅलो युवराज सेलर कुठे गेला? हा जरा अनम्यूट करता तुम्ही प्लीज. अरे किती वेळ झाला, आता आलाय. तुम्ही लेक्चर प्रत्येक अटेंड करताय का युवराज? युवराज, डोंट से सॉरी, आय एम जस्ट आस्किंग. लेक्चर अटेंड करत नाही का? आज काय गेस्ट लेक्चर म्हणून आलाय काय माझ्याकडे? एनसीएमच आहे ना तुमचा विषय युवराज? ऑकेजनली तुम्ही अटेंड करताय, बर. मग आज तुम्हाला इच्छा झाली का इलेक्ट्रॉन बीम मशीन शिकायची? ओके, मग तुम्ही काय हे जर IHP चा सब्जेक्ट दिलाय का युवराज? तुमचा इलेक्टिव्ह नो म्हणताय, बरं मग कुठला सब्जेक्ट कुठला ते तर सांगा मला. NCM इलेक्टिव्ह आहे का IHP? माहित नाही. बरं जाऊ द्या, टाइम वेस्ट घालत नाही रिलेटेड. ऐकायचं तर ऐक भाऊ, माझं काही विचार माझं काय म्हणणं नाही. ओके हा. हा कोटेड व्हॅक्यूम का पाहिजे आपल्या मशीन चेंबर मध्ये? सो इट इज कॉल्ड द व्हॅक्यूम चेंबर ऍक्च्युली. समजलंय सगळ्यांना? प्रणय दिसले? प्रणय
यस सर, यस
हॅव
सर.
कळाला?
हा सर, बॅकिंग मटेरियल जरा सांगा की.
हा हा, बॅकिंग मटेरियल काय तुम्हाला म्हणतो की आपल्या वर्कपीसच्या मागच्या साईडला बॅकिंग मटेरियल आपण वापरतो. ओके, आणि ते केमिकल मटेरियल असणार आहे. ओके, केमिकल बॅकिंग मटेरियल वापरतो. आणि ज्या टाइमला तुमचं वर्कपीसवर हिटिंग चालू असणार म्हणजे टेम्परेचर राईज होतं ना, तर म्हणजे काय हीट वाढते तिथं. ओके, आणि ते होल पडत जाणार. मग त्या टायमाला त्या तुमच्या बॅकिंग मटेरियलचं पण हिटिंग होणार. ओके, काय होणार? हिटिंग होणार. आणि ते आहे केमिकल मटेरियल. मग हिटिंग झाल्यामुळे काय होणार? त्याचं हाय वेलॉसिटी गॅसेस तयार होणार. ओके, आणि हाय वेलॉसिटी गॅसेस झाल्यानंतर पुन्हा काय होणार? तर त्या व्हॅक्यूम मधून ते हाय प्रेशरनं बाहेर पडणार तुमचं काय बॅकिंग मटेरियलचा गॅस. आणि ते बाहेर पडत असताना जे मटेरियल रिमूव्ह झालंय तुमच्या वर्कपीस सरफेस मधनं वरनं, त्याला म्हणायचं वेपराइज्ड मटेरियल. मग ते वेपराइज्ड मटेरियल सुद्धा तुमच्या त्या हाय प्रेशर बॅकिंग मटेरियल जे बाहेर पडणार आहे त्याच थ्रू बाहेर पडणार. ओके, त्यामुळे काय होणार? जे आता धरून चाला की तुमचं मशीनिंग झालंय, होल पडलंय, पण ते मटेरियल नाही बाहेर पडलं तर काय होणार? तुमच्या वर्कपीस सरफेसवर एक लेअर तयार होईल का नाही, त्याला म्हणायचं रिकास्ट लेअर. करेक्ट. मग ते रिकास्ट लेअर जर मला रिड्यूस करा असेल तर हाय प्रेशर थ्रू ते मला मोल्टन मटेरियल किंवा वेपराइज्ड मटेरियल मला बाहेर काढावं लागणार आहे. मग त्यासाठी बॅकिंग मटेरियल वापरणार. आणि त्या बॅकिंग मटेरियल काय होणार? ते हिटिंगमुळे हाय वेलॉसिटी गॅसेस तयार होणार आहे. ओके, हाय वेलॉसिटी गॅसेस तयार होणार. आणि ते जनरेट झाल्यानंतर काय होणार? इट विल कमिंग आउटसाइड विथ अ व्हेरी हाय वेलॉसिटी, सॉरी व्हेरी हाय प्रेशर. ओके, आणि हाय प्रेशर बाहेर येत असताना इट विल एक्सपिल द व्हॉट एव्हर द वेपराइज्ड मटेरियल इज देअर नो ऑन युअर वर्कपीस, दॅट इज कॉल्ड रिकास्ट लेअर. ओके, आणि ते रिड्यूस होणार. त्यासाठी ते आपण बॅकिंग मटेरियल वापरतो. आणि इट इज केमिकल बॅकिंग मटेरियल. डोंट फॉरगेट दॅट. आता whether I have given the satisfactory answer or not, समजलं का आता
Yes
का
sir,
वापर?
yes sir. हा.
गॉट इट? नाहीतर काय होणार? आपण मटेरियल धरून झाला किंवा मटेरियल आपण मस्त रिमूव्ह केलेलं आहे, पण ते तिथंच लेअर आहे, तर काय होणार आहे? तिथं असं हायच राहणार. त्याला म्हणायचं रिकास्ट लेअर. तिथंच तयार होणार ना, म्हणजे सॉरी तिथं लेअर एक तयार होणार. मग ते आपल्याला नॉर्मली फॉर एक्झाम्पल जसं की आपल्या ॲब्रेसिव्ह जेट मशीनिंग वगैरे मध्ये कसं होतं? त्या ॲब्रेसिव्ह पार्टिंग मटेरियल रिमूव्ह होते, बरोबर आहे. सायमल्टेनियसली ते आपण रिमूव्ह पण होऊन झाला ना, बिकॉज ऑफ हाय वेलॉसिटी. ओके, किंवा आपण एअर वगैरे वापरली तर ते मटेरियल रिमूव्ह झालेलं मटेरियल बाहेर काढायचं, त्याला म्हणून एक्सपिल म्हणतो आपण ते. ओके, अजून कोणा काय शंका प्लीज विचारत जावा. And same diagram you will get in the VKGN book. Same diagram I have taken. Okay. अजून मी रिपीट करतोय वन्स अगेन ना, प्रत्येक लेक्चर मी का विकेजन बुकचं नाव घेतोय, ॲडव्हान्स मशीनिंग प्रोसेस बाय विकेजन. तर ह्या ऑथर थ्रू म्हणजे डॉक्टर विकेजन फ्रॉम IIT कानपूर, त्यांच्याच ह्या बुकवरनं दुसऱ्यांनी पुस्तकं लिहिली ती. ओके, तुम्ही कुठं बी जावा तर तुम्हाला ह्यांचंच बुक रेफरन्स मध्ये भेटून जाईल. ओके, किंवा तुम्ही गॅरे बिंडेक्सचं ॲडव्हान्स मशीनिंग प्रोसेस बाय गॅरे बिंडेक्स म्हणून एक बुक आहे, ते पण तुम्हाला भेटून जाईल. गुगलवर त्याचा हे गुगल बुक आहे. ओके, किंवा तुम्हाला अजून एक भेटून जाईल की हे नॉन ट्रॅडिशनल मशीनिंग प्रोसेसेस बाय हसन ई लोफी. ओके, त्याची जरा लँग्वेज थोडी डिफिकल्ट आहे ह्याच्यापेक्षा ते. आणि तुम्ही टेक्स्ट बुक जर वापरलं तर काय होणार आहे की साधं सिम्पल की फॉर एक्झाम्पल डिप्लोमाच्या बुकमध्ये वर तुम्हाला काय भेटून जाईल की इलेक्ट्रॉन्स बीम आर बंबार्डेड ऑन द वर्कपीस आणि मटेरियल रिमूव्ह विल टेक प्लेस. पण ते इलेक्ट्रॉन बीम कुठून तयार झाले हे महत्वाचं आहे. मग ते इलेक्ट्रॉन बीम तयार होण्यासाठी तुम्हाला कॅथोडची गरज आहे आणि तिथं मग ते टंगस्टन वापरावं लागणार आहे. बरं, त्याला हिटअप करण्यासाठी आपल्याला काय तर सोर्स लागणार आहे. मग आपल्याला माहित पाहिजे ना हाय वेलॉसिटी लीड वापरलाय म्हणून. तर ओके, आणि ते म्हणजे निगेटिव्ह टर्मिनल असणार आहे. मग आपल्याला पॉझिटिव्ह टर्मिनल पण पाहिजे म्हणून ॲनोड दाखवायची गरज आहे. ओके, आणि ते फिल्टर करण्यासाठी मग कॉइल वापरलेले. हे प्रत्येक क्वेश्चन कुठला प्रत्येक पॉईंट किंवा कुठलाही पार्ट एलिमेंट आहे तिथं आपल्याला क्वेश्चन आपल्याला मनात आलाच पाहिजे ना की हा एलिमेंट का वापरलाय, त्याचं फंक्शन काय आहे, किंवा इलेक्ट्रॉन्स तयार कुठनं होते हे महत्वाचं आहे ना. सो फॉर दॅट पर्पज आय एम गोइंग इन डिटेल अँड फॉर दॅट पर्पज ओनली आय एम रेफरिंग द रेफरन्स बुक. ओके, अँड अगेन दॅट इज अ स्टँडर्ड रेफरन्स बुक. ओके, मुद्दा मी तुम्हाला टेक्स्ट बुकचं कधी नाव घेत नाही. ओके, इन डिटेल मध्ये गेलं पाहिजे. ओके, सगळ्यांना समजलं का? say yes or no in the chat box only, you can say no problem. In the chat box say yes or no. Gayatri Joshi, have you understood?
Yes, sir.
Sonone, Dhanasri Sonone,
Yes, sir.
Aditya Motevar, then Nanasaheb Shinde, understood? आदेश बनकर, अनिकेत बनसोडे. ओके, ओके, आता आपल्याला वर्किंग प्रिन्सिपल आपल्याला माहित झालं. नाव लेट अस डिस्कस द सिस्टीम. पूर्ण सिस्टीम डिस्कस करू आता आपण. नाव यू कॅन सी हिअर वर्किंग प्रिन्सिपल साठी हे वापर बघितलंय. ओके, 1 मिनिट. व्हॉट आय विल डू, प्लीज 1 मिनिट बोलले. पाणी पितो. आणि हे एक विसरू नका की ऍडव्हान्स मशीनिंग प्रोसेसेस मधली एकमेव इलेक्ट्रॉन बीम मशीनिंग एकच प्रोसेस अशी आहे की जिथं व्हॅक्यूमची गरज आहे. ओके, अदर कुठल्याही ठिकाणी लागणार नाही. Just we'll see the one animation video how this electron beam machine works. Okay, you can see this is a vacuum chamber. Actually there is voice, but from this PC it is not possible to give the voice. Okay, so this is your grid cup, that is cathode filament. Okay, and to hit that cathode filament, we require the high voltage cable. That means the high voltage lead. Okay, then we have the anode. Okay, circuit will come. Then diaphragm. Then optical wave system. That diaphragm is whatever I will give the expression in that your wall coil. Okay, the magnetic lens and deflection coil, vacuum chamber and workpiece. Okay, now see how the वर्किंग प्रिन्सिपल विचारलं किंवा तुम्हाला सिस्टीम विचारलं तर सेम डायग्राम काढा, नो प्रॉब्लेम. Now once your power supply will start, no, then your this cathode filament will start to heat up. Okay. Okay, then electrons beams will generate. That is negatively charged. Okay, then it will filter out from that diaphragm, and if you want to see that vacuum chamber, then optical viewing system is there. And to concentrate on the small area, this electron beam, to reduce the diameter, we require the magnetic lens. Okay, and to avoid the deflection, so deflection coils are used. See, the small diameter electron beams are bombarded on your workpiece. Okay, and whatever the high velocity stream of the electrons is there, no, so it will bombard on the your workpiece, and through that bombardment kinetic energy is going to convert into heat energy, and due to that heat energy temperature of the your workpiece surface will increase, and through that rise in temperature melting and vaporization action will take place, and due to that material removal will take place from the your workpiece. Okay. Just a minute, I will show one more. Major applications we are going to see, but here just quickly I will show the how the electron beam drilling process takes place. This one industrial video. अच्छा, ह्यात काय समजेना एक मिनिट. This is electron beam welding. See, a vacuum chamber, vacuum pump. Now that electron guns is what? That your cathode filament. It's the animation of the that electron beam welding machine. Industrial. Like this actual. This here is evacuated from the chamber. Okay. Evacuated means बाहेर काढले. So vacuum. So this is your cathode and anode. Okay. This is the main. So this is called your vacuum. Sorry, your gun, electron gun. See, lens, then deflection coil, and then our workpiece, and to weld that workpiece. Okay, okay, and that is that heat radiation, then radiation. Okay, and see now how the holes are generated. I think this is a good demonstration of our electron beam welding. See, molten. Okay, so this welding section they have shown different root and the molten material. Okay, and the electron beam. And then you can take out your uh, finished component, we can call, or final component, machined component, we can call. Okay, let me check another one. So I forget to mention that already this at YouTube you will get one my small that not small 18 minutes my video that about this electron beam busting. Okay, it's a link tomorrow today I will share. Okay, this lecture. I want to show actual. Okay, let's go back. Go back. इलेक्ट्रॉन बीम मस्टिंग बद्दलचा युट्यूबवर ऑलरेडी माझा व्हिडिओ आहे मी तुम्हाला ते पाठवतो उद्या आज लिंक शेअर करतो लास्ट सेमिस्टरला शिकवत असताना ते बनवलेलं आहे अच्छा ओके I will see this. Now let us discuss the elements of this electron beam machining system. Okay, so here you can see in this slide there are different elements of electron beam machining system I have shown. So first one is the electron beam gun. Okay, then second one is the power supply, and the third one is the vacuum system and machining chamber. So these are the three main elements of the your e-beam system. Okay, so this electron beam machining, electron beam gun. So it operates in the pulse mode. Okay, it operates in a pulse mode. So there are some biased electrons are used. So by controlling this, biased electrodes are used. So by controlling this electrode, you can generate the electron beam. So pulse electron beam you can generate. So it that electron beam gun produces the focused electron beam on a that predetermined location. So there is a superheated cathode is there, okay, in that electron beam gun, and it usually it is a tungsten filament which is heated up with a very high temperature. Okay, I repeat, in electron beam gun there is a superheated cathode is there. Okay, and it that superheated cathode means what? It is usually your tungsten filament. Okay, and which is heated up with a very high temperature, or you can use a solid block of cathode. Okay, which is heated up by the radiation of the filament. So but both things are possible. So because of this heating up this electron, this cathode electron that cloud are actually generating surrounding that your cathode, okay, the filament. So this electron cloud, because of this they are negative charge, no, it is expelled because of the repulsion force of your cathode. From your cathode it will expel, and it is attracted toward the as I mentioned toward the anode. Okay, it is attracted by the opposite charge, that is anode, and then after that it passes through the magnetic lens, correct? So when it is passing through the magnetic lens, no, so that converging beam pinpoint at a location can be generated. So this beam is actually pinpointed towards a small location when it is passing through that your magnetic lens. Okay, and also it defect and the mega round beam. Okay, so this our components of this magnetic lens. Okay, so also the this stray electrons are moved through the by using the your magnetic lens. Okay, they scatter होतात ना बाजूला, so that you can remove, and the diameter of the beam is further reduced with the help of the our magnetic lens. Okay, then this power supply. Okay, this three element. So this power supply generates a high voltage. So it is around 150 kilovolt it generates. So because of this high volt, electron beam gun generates the electrons. So this electron beam machining gun is a powerful system. Okay, so it is operated at a 12 kilowatt. So pulse energy as high as that is a 120 joule per pulse that can be generated from this electron beam machining gun. Okay, so computer control of the process variable can be generated. So all these are parameters are controlled by the your computer control system. So high power densities are required for melting and the evaporation of the metal, and it will give the high metal removal rate also. Okay, so high power density is required. So we can take using the power supply, and if you have the high power density, then melting and evaporation of that your material it will take place, and will get the high material removal rate, and the huge amount of energy by the collision of these electrons are generated. So material machined mostly by the vaporization of this material. Okay, now third one, this vacuum chamber and machining chamber. Okay, so already I told this machining chamber is a vacuum, as the beam actually travels during the machining, so it may collide with the air molecule. So that is why to avoid the collision of this electron beam with the electron with the air molecule. So this machine chamber is made up of the made vacuum. So pressure inside the machine chamber is maintained 10 to the power minus 5 to 10 to minus 5 torr. Okay, so because of this vacuum, so there is no oxidation of this your tungsten filament. Otherwise, if it is not vacuum, so whatever this oxygen molecules are there inside the air, it will oxidize the your tungsten filament. So which is heated up so to a very high temperature. So there is no collision of these electrons due to the your vacuum, and the air molecules will not be there. So no loss of energy of this energy. So no loss of energy of the your electrons. Okay, because of this your vacuum chamber. Okay, so these are the main elements. Now then let us discuss the process parameters. Okay, now the question is that what are the different process parameters for this electron beam machining process? So this process parameter are the first beam current, then pulse duration, lens current, okay, then beam deflecting signals. So these are the different process parameters, and I am going to talk about this. Okay, so there are the four important parameters for this electron beam machining process. So talking about this first one, this beam current, it may be it varies from 100 microampere ampere to 1 ampere. So this beam current actually governs what is energy per pulse is there. It governs the energy, beam energy per pulse on the your workpiece surface. Higher value of this beam current will generate a high beam energy per pulse. Okay, and it will generate the high material removal rate. Okay, this is just it's a relevance of this or importance of this beam current. Okay, I repeat, higher value of this beam current will generate the high beam energy per pulse, and it will generate the high material removal rate. So by changing this beam current, you can change the beam energy, or you can change the material removal rate or the workpiece on that workpiece surface. Okay. Then talking about the pulse duration. This duration of this pulse, it varies from 50 microsecond to 10 millisecond. Okay. So a longer pulse duration will generate the wider and deeper holes. So if we put this pulse on the for a longer duration of the time on the workpiece surface, so obviously it will generate the wider shallow hole, but deeper holes, because it is kept on the workpiece surface at a certain time for a long period of time. Okay, so it will generate wider and deeper hole, and it affects this pulse duration. Okay, also affect the heat affected zone on your workpiece surface because of this heating of this surrounding material, because long time of duration we are providing. So due to that, heating of the surrounding material will take place, and it generates the higher heat affected zone if this pulse duration is increased. Okay, so this recast layer, that the dimension of that recast layer in case of the electron beam machining process is normally 25 to or around 25 micron will be there. Okay, then next parameter is the lens current. Now lens current, now it determines the that working distance and the focused beam size. Okay, working distance and the focused beam size. So beam diameter, it determines the lens current. Sorry, beam diameter, it determines the lens current. Okay, it determines the lens current. Okay, and the beam diameter also, and also it determines the working distance, and also it determines what is the diameter of the your beam. Okay, so this lens current, it will determine your working distance and the focused beam diameter, beam size. It is called focused beam size. Okay, so This is also important. And the fourth process parameter is the beam deflecting signals. So beam deflecting signals, it affects the hole shape, straight or the tapered holes, determined by the position of your focal point below your top surface of the workpiece. So this holes, whether it will be straight or the tapered, it depends on the your this focal position, focal point. Okay, focal position, focal point of the your beam, whether it is just the top surface of the your workpiece or just below the workpiece surface. Okay, and for non circular hole, no, it is just for non circular hole, a beam moment can be programmed. Okay, that for non-circular hole your beam movement can be programmed. So other than circular hole, this beam movement can be programmed. Okay, so these are the process parameters. Let us now see the how to calculate the material removal rate in case of this electron beam machining process. So it is calculated by the with the help of this formula. MRR, that is the material removal rate, is equal to eta into P divided by W. Okay, now here eta means what? Your cutting efficiency. Okay, cutting efficiency. Okay, and usually it is below the 20%. And now MRR means what? Rate at which material removal, that workpiece material vaporized. Okay, that is called MRR. Okay, and to calculate that we have the formula. Again, this formula we came from the different researcher. Eta into P into W. Sorry, P divided by W. So eta is the cutting efficiency and it is usually below the 20%. P is the your power. Okay, joule per second. And W is the specific energy. It is in joule per centimeter cube. And it is it is required to vaporize the workpiece surface. Hello, काय सर लेक्चर चालू आहे. Okay, I will call up to 1 hour. 12. Okay, so that W means what is the specific energy and that is required to vaporize the workpiece surface. Okay, so that is the main formula. Now again, how to calculate that W? For that purpose also we got the one formula. Again, from this formula we got from the literature review. That means from different researcher papers we got this. So to calculate that W, you can use that formula, Cp into Tm minus Ti plus Cp Cp yes is there and then Cp L is there. Now that suffix yes means what? It stands for the it indicates the solid and the liquid states. And then plus HF and HV. Now Cp means what? We know that specific heat. Tm means what? Melting point temperature, and Tb is the boiling point. Okay. And HF, that is the latent heat of fusion, latent heat of vaporization. So using that formula you can calculate the specific energy. Okay, so this we got from the research papers. We got from the different research papers, this formula. So for this our knowledge purpose, we should know the formula. Wait, 1 minute, I will tell the name of that paper also. Okay, so you will get this detailed references in this book also, that Vikajam sir book, Advanced Machining Process. Okay, Okay, so this is about the material removal rate. Now just now we'll go for the further, that is the process characteristics about this EBM, that is called characteristics of this process. So this process, you can see, so this process can be used for the, as I already mentioned, that for the conductive as well as the non-conductive material like nickel, copper. Now this material means also workpiece material. So like nickel, copper, aluminum, ceramic, leather, plastic, for all type of any kind of material can be machined by this process. Okay. Now at the entry side of the your beam, no, it is observed that there is a burr. Okay, at entry side of the beam, it is observed that there is a burr on your workpiece because of this recast layer of the vaporized material are coming outside. No, so vaporized, while this vaporized material are coming outside, no, so it actually generated a recast layer at the entry side of also. Okay, so this, because of this recast layer, small amount of burr are actually visible at the entry side of your workpiece surface. Okay, so this at entry side of the beam, small size of burr, solidified layer left out. So workpiece properties are like physical, mechanical, metallurgical, that will do not have a significant effect on the your performance of this electron beam machining process. Okay, so workpiece property does not have any effect on the performance of this electron beam machining. This is one of the important. One is the your regarding material, and the second one is about the that property. And for your information, that process characteristics, that is at intersect there is a burr formation due to the solidified recast layer. Okay, then a hole diameter. Okay, and the hole diameter as low as 0.1 to 1.5 mm, and large depth 10 mm, and the high aspect ratio of 15:1 can be generated from this workpiece surface. Okay, this is a process capability. You can call capability of the characteristic. So you can make hole, that small diameter hole around 0.1 to 1.5 mm diameter, and large depth 10 mm depth. Okay, along with that high aspect ratio up to 15:1. Okay, so that can be generated using this machining process. Again, there is no mechanical force because this electron beam machining. So this tool does not touch the workpiece surface. So there is no mechanical force. So any kind of fragile, brittle, thin, or low strength component can be easily machined using this process because of no machining mechanical force. So hence there is no workpiece tool material does not touch the your workpiece surface. Okay, tool material does not touch the workpiece surface. So there is no distortion of the workpiece. Okay, due to the mechanical force. Mechanical force नाही तर distortion होणार नाही. So this another process capability, that is no distortion due to the mechanical forces. Okay. Then off-axis holes also can be easily made or generated by deflating your beam. Okay, off axis means outside your axis. So off axis holes also can be easily generated by deflating your beam, but there is a thermal residual traces is generated because there is a huge temperature gradient is there. No, so because there is a huge amount of temperature generated locally at the on the workpiece surface where this beam is falls. Okay, so off-axis holes can easily made, but residual thermal residual traces are there. Okay, due to the high temperature gradient. Then again important that very high cost of equipment. Okay, very high cost of your equipment. Then we require the skill operator. Okay, then that machining edge quality. Okay, machining edge quality. So what are the machining edge quality is there, no? So that is totally depend on your thermal property. Okay, machining that quality, okay, edge quality, it depends on the your thermal properties of the your workpiece material and the pulse energy. Okay, I repeat, machining edge quality, it depends on the thermal properties of your workpiece material, pulse energy. Okay, and how much pulse you are giving, how much energy you are giving per pulse, also affect your quality of the machine edge. Okay, again that heat affected zone, HHZ, heat affected zone in case of electron machining process, it depends on the pulse duration and the your hole diameter. Okay, so this heat affected zone, it depends on the pulse duration and the your hole diameter. So these are the process characteristics about the our electron beam machining process. Now let us discuss the application, last part. Now there are various applications are there of this electron beam machining process. So firstly, it is most popular for aerospace, insulation, for food processing, and the chemical and the cloth industries. Okay, I repeat, this electron beam machining process, it is mostly more popular for aerospace industries, insulation purposes, industries, then food processing and the chemical and the cloth industries, etc. So hundreds to thousands of holes can be generated on your workpiece surface in a simple and a complex shaped holes can be generated on your workpiece surface. Okay, I repeat, hundreds to thousands of holes. Okay, yeah, again in that simple and complex shaped holes can be generated in your workpiece surface. Okay, again perforation of the sheet on a complex shaped and the difficult to machine materials can be generated. Okay, perforation of the sheets. Okay, that activity also we can perform using this laser beam machining. Okay, for example, okay, that means the drilling of the thousands of hole diameter less than again 1 mm in a thin plate. Okay, which is used for the turbine engine combustor dome. Okay, turbine engine combustor dome. So there we can use this. Okay, I can show here. You can see here. Okay, so thousands of holes, again diameter less than 1 mm, we can drill by using the electron beam machining process. Okay, and normally again this you can take the example of that thousands of holes in a thin plate which is used for turbine engine combustor dome. Okay, so many thousands of holes less than diameter less than 1 mm in cobalt alloy. Okay, cobalt alloy material, cobalt alloy fiber, a spinning head of thickness 1 mm can be generated. Again, drilling by this electron beam machining, it's claimed 100 times faster than the your EDM process. Okay, this is a important advantage. Thousands of holes we can generate, and that drilling is 100 times faster than the your EDM process. Then holes in your filters and the screens. Okay, it is possible using this process. Okay, now again this holes in filters and screen, this is application in food processing industry. Again, fine gas orifice is there, no? Fine gas orifice in space nuclear reactor. Okay, so for that purpose also we can use this electron beam machining. Then holes in wire drawing dies, holes in wire drawing dies. Okay, that also we can generate using this electron beam machining. Then cooling holes in the turbine blades. Then metering holes in injection nozzles of your diesel engines can be made by using this electron beam machining process. Okay, metering holes in injector nozzle of your injection nozzle of your injector nozzle of your diesel engine can be made by using this electron beam machining process. So now you can see here there are so many holes are generated. All these holes diameter is a circular hole diameter is 0.9 mm, and hole density you can see 4,000 holes per centimeter square. Okay, 4,000 holes per centimeter square, and workpiece material is a stainless steel. So this is possible using this electron beam machining. Again, thickness of the workpiece material is the 0.2 mm, and the time required per hole is 10 microsecond only. So here again you can see another pattern. Again you can see very small diameter holes around 6 micron is generated by this electron beam machining. Okay, here hole density is 20,000 holes per centimeter square. Okay, 20,000 holes per centimeter square on stainless steel workpiece material of thickness 0.012 mm and distance is 20 mm. 70 micron, and the time is 2 microsecond per hole. So this kind of pattern or of the holes are generated on the workpiece surface by using this electron beam machining. Okay, this is a very important example. Okay, another one. So here you can see small holes. Here you can see small holes which is generated on the workpiece surface, and here you can see the your macro graph of the holes, cross section of the cavity in the chromium molybdenum steel formed by the single pulse. Okay, this cavity is generated. Okay, here whatever the hole we have drilled now by using your electron beam machining, so it is 0.1 mm diameter is there, cross section you can see. Now again this diagram it is quoted by the one of the author, and that paper is 1967 paper here, and another this one taken is there, no. So this here I have shown the cross section of the cavity, and that cavity is made in the chromium molybdenum steel formed by the in a single pulse. Okay, and this diagram I have taken from the one of the research paper. Okay, actually this we got from the one of the NPTEL course, and that paper is 1976. Okay, so see, still research this advanced machining process. Okay, still researchers are doing the research in this field. So you can also another diagram I will show. So here also you can see hole drilled in a metal alloy sheet. So this kind of holes are generated by this process. So here also this cross section of the cavity made up by the single electron beam pulse in chromium molybdenum steel, which is generated by this electron beam process. Okay, see the cavity here I have shown, and diameter of the damaged layer also they have shown, and that cavity diameter is there here 0.01 mm, and here hole you can see 125 micron hole drilled by this EBM in the metal alloy sheet. So with this I'm going to conclude this today's topic, electron beam machining process. Okay, thank you. I hope you understand this total process of the electron beam machining. Now I request you, please Draw this diagram. This is important diagram. All of you, please draw this diagram. Please. Okay. Same diagram is there. Just I have taken the. Whether it is visible.
Yes, yes.
Please draw this diagram. Diagram is important. Now only that plasma arc machining and ion beam machining, two processes are remaining from our this chapter number 5. Okay, and again from our advanced machining. And in the 6th chapter, we are going to see the introduction to coating technology. Actually, that coating technology, it is belongs to the surface engineering stream. Okay, so again that in detail I will teach. Don't worry. over. And whatever that upper part is shown, no, that red chamber, okay, upper, it is called electron beam gun, from start from the your high voltage, that lead, okay. Then we have the cathode grade and all these things, okay. Up to that depletion coil, no, all the elements. So it is called the electron beam gun, because from that portion, or the from that uh, elements, all the elements, we're getting the electron beam, no, it is called the electron beam gun. In many book, or in many PDF, if you search Google out, no, you will get the different diagrams, okay, but all the elements are same. If EBM equipment, if anyone asks, you can draw this, no problem. Working principle for same diagram, electron beam gun, you can draw this, no problem. Over. Uh, uh, I will show the diagram of the electron beam gun. Okay, so this is the diagram, electron beam gun. You can see here we have that high voltage supply, okay, to the cathode, that is the high voltage lead we can call. Then we have the that cathode filament, it is called cartridge, okay, cathode tungsten filament, okay. Then we have that biased grid and anode, okay, same. Then we have that diaphragm, or we can call the that for filtering purpose, a vacuum throttle wall is there, okay. Sorry, for vacuum it is here, okay. This one is the diaphragm. Then uh, for gauge, that vacuum throttle wall is there, okay, for vacuum, okay. Porto for diffusion pump is there. Then for vacuum gauge, the magnetic lens is here, okay. Then Uh, so this is called the electron beam gun. Okay, to produce the you can draw this diagram also for your our knowledge purpose. We should know. Please start draw this diagram also. Actually, this electron beam is there. No, that is you can call it is a heart of your electron beam machining process. Okay, and the basic function of any electron beam gun are to generate the free electrons at the cathode. Okay, and accelerate them to the accelerate them to a sufficiently high velocity. That means a high velocity, and to focus them for a small spot size. That means for that purpose, in electron beam gun we have that magnetic lens also. Okay, so here cathode is generally made up of the tungsten. Don't forget. Okay, and such cathode filament are heated. Okay, uh, with the help of your that high voltage lead. Okay, and that temperature may be around 2500 degrees Celsius. Okay, and due to that heating, it will leads to the your that thermoionic emission of your electrons, and that what are the combination of that repelling force are there no from the your negatively charged cathode or negative cathode. So that repelling force from your negative cathode and the attracting force from the your positive anode. Okay, it causes the free electrons to be accelerated and direct towards your workpiece. That is fun, simple funda. And another one major requirement of this EBM operation of your electron beam gun is, you know, to maintain the dissolved vacuum also. Okay, for that purpose, this gun is important. Okay, please draw this diagram. Now, simultaneously, I will just note down your attendance. In the next lecture, we are going to start the new one, we'll start the plasma arc machining. And the popular word for this machining is the plasma arc welding. Okay, welding, other that like this, our laser beam cutting is there, no? If anybody having any doubt, please ask me so that we can discuss that also. Please don't leave this meeting. Yet I have not taken attendance. If you have left, then you will be absent. I'm not going to count your name here.
over okay. Shall we stop here, or may I continue for again for 10 minutes? What to do?
Stop, sir.
Abhinay, stop
Stop,
करायचं?
sir. Yes.
Okay, okay, okay. Here we'll conclude today's lecture. Okay, see you in the next lecture. Thank you very much. You can leave now meeting.